So in question 2, they want to find which ones of those are factors. Okay, so if you're wanting to find a factor, the word factor here implies the remainder is 0. So if the remainder is 0, then it's a factor. And again, we could use synthetic division or the remainder theorem. So for the first one, I'm going to do both. Because I think for the first one is the only one that the remainder theorem or synthetic division are about equal. Easy to figure out, about the same. After that, when the numbers get bigger, I'd probably lean towards synthetic division. But if I put this in brackets, whole thing in bracket, and I say let p of x equal this, then using the remainder theorem in A, you plug in opposite side p of -1. And that would be -1 cubed minus 6 times -1 squared plus 5 times -1 plus 12. A negative cubed will be -1 minus a negative squared is positive, minus 6 minus 5 plus 12 equals 0. So x plus 1 is a factor. And what that means is that we can maybe factor this completely. I'm also going to do this one, I'll switch colors here. I'm also going to do this one with synthetic division to see that you would also find out it's a factor with synthetic division. So we'll go purple here. I set up things with synthetic division. Is it in the right order? Yes. Is anything missing? No. I don't have to add any zeros. And with synthetic division, the number you put outside, if you're divided by x plus 1, is the -1. Okay? Notice your signs are switching back and forth a fair bit in this unit. That's one of the things that you're going to have to be paying attention to. Like, do I put a +1 or -1 if I'm dividing by x plus 1? Then we bring the number down. Bring down the 1, multiply and add, multiply and add, multiply and add. And if you get the remainder of 0, it matches up with what we got with our remainder theorem. So there's 2 ways you can find out the remainder. Either using the remainder theorem or with synthetic division, whatever that last number is your remainder. And again, if the remainder is 0, that tells us that x plus 1 is a factor. Now, before you go to B, I would like you to just leave a little bit of space underneath the synthetic division. We're going to do something there at the very end of the question. So we're going to leave some space, and then we'll go to B next. So I said I like the remainder theorem when the number's a 1. Any other number, I find the synthetic division is usually better. Not always, but usually. So for the next one that we have, which is x minus 3, I'm going to set up the synthetic division for that one. Which is exactly as the synthetic division set up for the last one. But this time I'm checking if x minus 3 is a factor. So I would put a +3 outside. Bring down the 1, multiply, add, multiply, add, multiply, add, and we get that remainder of 0. So off to the side here I can write, so x minus 3 is a factor. So we can find out if something's a factor if we get that remainder to be 0. And once again, I'm going to get you to leave a little bit of space under this one. And then we'll do part C. Again, the same setup for synthetic division. 1, -6, 5, and 12. This time in part C, we're checking if x minus 4 is a factor, which would put a positive 4 out front here. Bring down the 1. Multiply and add. Multiply and add. Multiply and add. And oh my goodness, another 0. So x minus 4 is a factor. Are they just giving us factors? Again, I'm going to get you to leave space under this one before you get to D. We'll do D quickly. Same thing. 1, -6, 5, and 12. And in D, we're dividing by x plus 4, so there would be a -4 out in front. Bring down the 1. Multiply and add. Multiply and add. Here's the first time that synthetic division has got us a little bit tricky with numbers. Our remainder is not 0. So on this one we can say, so x plus 4 is not a factor. In fact, if we called p of x right from the beginning, we have found factors. We found out that the first one, x plus 1, was a factor. So we could write that's one of the factors. The second one was x minus 3 as a factor. The third one said x minus 4 is a factor. So I know that p of x should equal this, but could it have more factors? Or is this actually factored completely? I'm going to zoom and view, like, look at what we started with. Oh, I thought I did. Okay. We started with, it's really tiny right now, but p of x was an x cubed equation, right? And if I scroll down, and I wrote the factors that we found, is that all of them? Or could there be more? If you multiplied that out, do you think that would get us exactly what we were looking for? Or do you think it would be off?
Exactly.
Exactly. What kind of things give you the hint that you think it would be exactly?
We have an x cubed and we have 3 x's, so when you multiply them all together, you'll have an x cubed.
Does it make sense that if I look at these first terms here, and you multiplied them all together, you would get an x cubed? If you added an extra factor, you would get to an x to the 4. That makes sense? Okay? So we are actually, by doing this question, we factored that completely. But right now, if I was thinking about this, I'd be like, so Mr. JR, do I just have to like keep trying ones until I find, if it's an x cubed, find 3 that works? If it's an x to the 4, do I just keep trying and trying and trying until I find 4 of them? Well, that could be a strategy, but that doesn't sound like a very efficient strategy. We're going to want to see if we can find an efficient strategy. And that's part of the reason I got you to leave some space after each of these. So we know this is the final answer. Keep this in mind. This is factored completely. Those are all the factors. I'm going to zoom back a little bit bigger so you can see it. After the first one, I said, can you leave some space? And the reason I wanted you to leave some space is because you could write the division statement. P of x equals, well, we divided by x minus 1, so x plus 1 multiplied by what is left from your synthetic division, and this is another reason why synthetic division is nicer than the remainder theorem in this situation, because it lets you write your division statement. And there's no remainder, so the dq, remember our division statement is dq plus r, and the remainder is 0, so that plus r doesn't matter. And it's just the divisor times the quotient. And had you written division statement, this is a quadratic, which you have factored before. Do you think you could factor that? Is it factorable? If it would be, does it make sense it would have to have an x and an x to give you the x squared? Are there two numbers that get you 12? Outside and inside make negative 7? Have to be 4 and 3, and both of them negative? And isn't that our final factored one? If you find one factor and you write the division statement, you might be able to just factor it on its own. You wouldn't have had to find these other ones, the 3 and the 4, with synthetic division. That's kind of cool. And check it out. Had you found the 3 first, under B, if we write our division statement, our divisor this time was x minus 3. What did we get as a quotient? X squared minus 3x minus 4 with no remainder. Does that factor? X and x. 4 and 1 with the 4 negative and 1. Yes, it does. Is that the exact same factors we found in the first part? Absolutely. It's really cool. And same thing would happen if you left space under the 4. P of
Sorry
x.
for the interruption. Any grade 10 students who would like picture retakes, or grade 10 students who did not have their picture taken yet, please go to the library now. That's grade 10 students who would like picture retakes or who have not taken their pictures yet, please go to the library.
So what we are discovering in this second one, if you get a remainder of 0 and it's a factor, that lets you write the division statement. And if your division statement has an x squared, you could factor that further because you already know how to factor x squareds. What we needed to do was to find one that worked first. Now I'm actually going to write out p of x just as it was here, because we're going to, so p of x was x cubed minus 6x squared plus 5x plus 12. Factored completely was x plus 1, x minus 3, x minus 4. Because if we look at patterns in the answer, those patterns teach us how to get the answer faster. First of all, I really like how someone told me that, hey, all of those are x's. We have an x cubed, so that most you could have was 3 factors. If I added a 4th factor, I would get an x to the 4th. So my first ones, my x, and my x, give me my first one here. Okay? Now, 1, x plus 1, x minus 3, and x minus 4 ended up being the factors. If I had started with this and nobody gave me a hint, how could you think of a strategy that makes sense to try these ones? But I'll tell you right now, x plus 7 would be a really bad choice for trying to figure out if it's a factor. I could do synthetic division right now for you and show you, yeah, if you tried x plus 7, it doesn't give a remainder of 0. How do I know that without actually doing the math? How does the equation tell me x plus 7 is bad, x plus 8 is bad, x plus 6 might be good? Because it's not a factor of the 12. The last number here is a 12. Notice our last number is here. What do they all multiply to?
12.
They'll all multiply to 12. Now, with 2 things you learn FOIL, right? With 3 things, there's something, I don't know how many letters we'd have to add to make an acronym for three things. It would be complicated. But you could do it because every arrow has to hit every arrow. And usually when you're multiplying these things, first you would multiply, choose, like we have here. First you choose two of them and get this. And then you would distribute all of these things afterwards, right? To get your final answer. But the last ones make the 12. The first ones make your x cubed. And so when we're asked to factor something completely, it's really important that we look at this last number and say, what are your possibilities? 1 and 12, 2 and 6, 3 and 4. And it could be plus 1 or minus 1. It could be plus 2 or minus 2, plus 3 or minus 3, plus 4 or minus 4, plus 6 or minus 6, plus 12 or minus 12. And as soon as you find one of them, you can do synthetic division and write your division statement. So, what have we discovered here? I'm going to give you the questions for this one. I already mentioned 12, but you can, it's 10, 8, and 12. 12 is a really good one for using the remainder theorem because the synthetic division doesn't work as well. But I also want you to turn to the and look at the bottom of page 18. And this box you can put a highlighter thing around it. It's called the factor property, which says, and the example right here probably shows it the best, that whatever the constant term of your polynomial is, if something's got to be a factor of it, it would have to work out that it's also a factor of that last term. Because our last numbers are going to have to multiply to give us 10. So options here are 1, 2, and 5. But you won't know if it's an x plus 1 or an x minus 1. An x plus 2 or an x minus 2. So we'll have to do a little bit of work leading into that. And that's going to lead us to our last example for today.